So let's keep going here. So we see that we need T3 and T2. We have T3 already, so we're good on that one. We do need to find T2 though. We have the three tools that I described earlier. We have ideal gas, we have isentropic processes, and we have conservation of energy. Here we're going to use the second case, an isentropic case, from 1 to 2. If we try to write ideal gas, we'd find that we don't have enough information. We don't know the pressure to, we don't know the temperature to, so that's 2 unknowns. That doesn't do any good. But we do know for process 1 to 2, it's an isentropic case of an ideal gas. And right now we're doing constant specific heats. So we have T2 over T1 equals, and we can write this case, V1 over V2 to the K minus 1. Because we know the ratio of V1 to V2 is 7. We know K is a property of our substance. In this case it's air, so K is 1.4. It's the ratio of specific heats. You could find those in table A1 or A2. And we know T1. So we can get T2. T1, 15 degrees. We have to put this into Kelvin, so that's, 288. Times V1 over V2, that's 7. I said K was 1.4, so K minus 1, 0.4. So that's going to get me T2. Based on that T2, I'll be able to go to table A17, get U2. So that's one important parameter. Based on knowing that T3 is 1273 Kelvin, we can get U3 from the same, from also A17. That's going to get us Qa. Some number kilojoules per kilogram. We'll do this calculation in a second. If we keep going forward, we see we need Q out. Energy balance for Q out occurs from process 4 to 1. Constant volume heat rejection. So Q out would be, the negative of Q out would be mass times the final state would be U1 minus the initial would be 4. This is for the process 4 to 1. So if I solve it for Q out, this would be capital Q out, sorry. If I divide by mass and then solve it for lowercase q out, it's just going to be U4 minus U1. I know T4, so I can get U4. I know T1, so I can get U1. I do not know T4. So I need to use one of my tools. Energy balance, ideal gas, or isentropic case. I don't know, let's see, yeah, I don't know P4, and I don't know T4, so ideal gas isn't going to do me any good because that's 2 unknowns right there. I do know that it's isentropic from 3 to 4. So I can write this equation, just like I wrote earlier. Nope. So I could solve it for T4. T3 was 1273. I know that V1 is the same as V4, it's constant volume heat rejection, and V2 is the same as V3. It's constant volume heat addition. So that is the inverse of what I need here. So this is 1/7, again to the 0.4. So that's going to get me T4 in Kelvin. That's going to get me U4 from table A17 in kilojoules per kilogram. And also, I know, let's see, T3 I've already gotten. T1 is 288 Kelvin. Based on that, I can get U1 from table A17. So once I have U1 and U4, I'm going to have Q out. Once I have Q out, I'll bring that up here. I'll have Q in and Q out. So I'll have the efficiency. Alright, I'm going to do the calculations, get the properties, put them back in here, and come back on the next video.